So hello. I'm here because Mark Durr couldn't be here. The slot was actually meant for him, and he would have talked about Lara Suite, a collection of software packages for high throughput experimentation, data documentation, experiment planning, and somewhere in his software package, the machine learning package I'm developing would fit. And the idea is to have something which, out of the box, allows to fit simple models, not so simple perhaps, but to have an optimized machine learning workflow to fit into this. And of course, for me, it's senseless to give his talk because he can do it better. But I felt somehow constrained by what he wanted to do, and so it's a compromise. And I try to embed what I talk into the things he would have said. The first thing has a strong intersection with what Jaro Abai was telling, that the idea is, of course, that if we have something which is automatic discovery, automated research, or self-driving lab or so, it's not that the human always triggers an experiment, but experiments trigger themselves. So you would have a cycle of designing experiment. And I put this preparing in it, even though it's conceptually not different from running the experiment, but in a high throughput lab, it often means that people spend days in the lab preparing everything for the robot to run. So when you evaluate how costly an experiment is, this plays really a role. We collect the data, analyze data, and design the experiment from data and models you have developed. That is kind of the idea of an optimized discovery, and there are a few examples of this. And Ross King is not here anymore, but his Adam the robot scientist was probably the most famous example that really worked and was fully autonomous. And then Eve also went in this direction in his lab. And he told me yesterday that there is a list of about 15 examples that are really working more or less autonomously. And I think in material science and chemistry, there is a trend. For protein engineering, that's not really the case. And I think we'll see why and what is missing. And the typical goal of not only about the main protein engineering tasks I have been looking at was actually enzyme engineering, to find enzymes with a specific catalytic activity or an increased enzymatic activity towards a certain substrate reaction. And this goal, once it is given, usually has been very successfully treated by a very primitive thing, which also has been automatized to a large degree. This is directed evolution. I'm not sure whether everybody is aware of it. It's quite stupid. You use your DNA you multiply it with error-prone PCR. It's just a randomized version of copying with errors, and you can adjust the error level by some concentration of manganese ions or so. And then you get wrong copies, and then you express them in a host, typically Bacterium E. coli, and then you screen for a certain enzymatic activity, and then you sort it according to the activity, and then you take the winners, and then you run the next round. And because there is virtually no model behind, it's very primitive, this is easily to automate. The interesting part is that the conceptual parts are perhaps the one that are least automized right now, whereas the running of the experiment, well, it goes. The truth of the matter is that some parts of the experimental circle in most labs are still done by hand, but they could be automatized as well. It's a question of what is cheaper. And students are often quite cheap. This has been largely automatized. Now, and it has no complex reasoning. Now the opposite, but this is the other method, which is probably the one biochemists love most, rational design. You have some hypothesis from your previous experience, from theory, about the functioning of a certain enzyme or an enzyme type. Then you can do molecular dynamics simulations, quantum mechanical simulations, all kind of stuff to get more information, to improve your hypothesis. And then the experiment is synthesized to prove or disprove your hypothesis. And of course, this only the experts can do. And then they say, okay, this can't be automatized. But of course, it can in a sense. It depends on what you mean. This rational design as it runs now, sometimes you can run the experiments then with the high throughput lab, but the rest of the thing is manual. Of course, you use tools, but the tools you run manually. And the data you look at with manual summaries, so it's all manual. Now, what would be a rational or semi-rational design with machine learning tools? Just have to look at the watch. Yeah. They would, according to me, would have two principal parts. One would be a predictive model. And this is a very abstract way of saying what a predictive model is. You take sequences, also DNA or amino acid sequences, substrates given by some chemical representation, SMILE strings, and conditions. And conditions is a complicated thing. The assay conditions, everything you know about how you obtain the information. And given all this, if you were an omniscient creature, you could predict what the probability distributions of the outcome should be. And of course, most of the models that are used are not really fully probabilistic. They predict, for example, only the mean and the variance, and sometimes only the mean. Okay. Then the second thing you would need is a generator. Why do you need a generator? Well, if you have 20 amino acids and you look at a protein of size 300, then you have 20 to the power of 300 possibilities, and it's just no reasonable way of exploring this space. So you need some generator which creates a tiny portion of that space, so tiny you can't really imagine the quotient. And there are many ways to do it. Most frequently, you have just specific residues where you want to mutate because you know something about them. Or there is this shuffling idea that you have building blocks, and you can then shuffle them, and then you have the n faculty possibilities to shuffle the building blocks, or choosing the building blocks and so on. Also the thing is, if you have a large database, Egon's data set was a product, among others, that you crawl information about putative aminotransferases, and then you cluster them, etc., and it's to select. So in principle, you can just have a selection of possible things you want to synthesize, and then you want to choose among this large collection. That's the other type of generator, and there are more possibilities. Okay, how would you use the components? You would generate variance, and then you would use the predictor to get the predicted activity distribution. Then you would rank the variance by some acquisition function which would take into account that it's not only a mean that you predict usually. Okay, that's the kind of the sketch. But of course, if predictor and generator are machine learning models, they would have to be trained. So how to get the data to train them well is another question. So what are the special conditions for machine learning under these conditions? The data availability to start, well, of course, in the running system, you would create new data. But first, when you try out your methods, you want legacy data. And the availability of legacy data is an odd thing in the domain. You have huge amounts of protein sequences with some unverified notations. UniProt has now, I think, 200 million, and a colleague in Oslo or Toronto, he claimed to have found 1 billion protein sequences in some database. So that's the amount we speak about. Then there are a large amount, natural proteins actually. Then there are a large amount of expert-created protein sequences, but it's less than 1 million that have been verified by experts among all those things that are in the UniProt database. Then we have a few medium-sized data sets with some specific real-value properties which are comparatively large. And there's this binding affinity of the protein GB1, which has been established by Wu in Arnold's group, I think, or later he joined them. And then there are the bulk of data is small data sets from individual labs for some individual purpose. And small really means small usually. Yeah, it's 20, 30, 40 enzymes screened for something. And the largest data set I have come by is Egon's data set, where he screened how many by now? Originally it was 450 or so. 800 putative transaminases on 50-something substrate combinations. And there's also another type of data which would potentially be rich, but it's not so much available. If you have liquid, if you have microfluidics, you can create examples in the millions, but you would have to sequence all the variants you create. And now it's comparatively cheap to have sequencing of millions of variants, but you normally don't get the whole sequence. So it's another complicated problem, but that's about the data situation. And of course, many of the data that are there are not in public database. You just have to talk to the people and in order to collect them. So for enzyme design, it means we have a small data problem. We have a huge amount of unannotated data, but a tiny amount of specific enzyme class annotated data. And then there are several answers to this. We can put up with a small data set. And what does it mean? Well, it means often that you do feature engineering. You try to get a few very expressive features with expert knowledge, and then you can just do linear regression, something simple, random forest, whatsoever, and it usually works fairly well if your features are well designed. But from a machine learning perspective, you would say, okay, feature engineering is always worse than learning the features. But it's what you can do. It's not bad. And then, of course, the thing I would love most, but I will come to why it's not yet so good, so easily feasible, is aggregating data sets. Now, if we can aggregate all transaminase data from the world, well, it will much improve our modeling. First of all, they would have to be put in some common repository, but for doing this, you would need a common standard which they comply with, and they would have to be annotated. We come to this with semantic information to query them. So that is really not yet there, but it should have been done long before, but hopefully it will be done. And we could change experimental practice. This is another point. We could just, in directed evolution, sequence more variants. Sequencing is now cheap, but usually they select the winners, sequence the winners, and don't sequence the losers. And this is just waste of energy. You have so much information which you throw away. What a pity. And then, of course, transfer learning. And that's the horse on which I bet a lot these days. You take representations from other tasks on proteins, unsupervised tasks or very simple tasks like predicting domains or so. Not simple, but comparatively. And then you use these representations as predictors for your enzyme prediction task. And the thing that is probably the most powerful but very difficult to realize is multitask learning, that you collect all types of different tasks and problems and then collect them into one model which is simultaneously trained for different tasks. And this is the one that eventually will win, but this will only come after this big aggregation, which has not yet happened. There are some initiatives which I would like to mention. Just a few days ago, Mark Durr brought me in contact with the Open Datasets Initiative, Align.bio.org, and they are obviously hosting a competition. And they are trying to collect datasets. So that's a step in the direction. And the thing that and I'd also like to recall TAPE, if you remember, that was presented in NeurIPS 2019. It's a package for testing transfer learning. And they provided a few of the public data sets on protein tasks, like the fluorescence data set and a few others. But something for enzymes would be a great thing, so that all machine learners can just try out what they can do with it. So one more problematic detail. Many data sets are unbalanced by design or by the decision to sequence only interesting invariants. That means for the problem, models will either be biased towards the successful variants, or, for example, in direct evolution, at least to sample one variant that is not successful for each one that is sampled. Something to make them a bit more balanced. Now I come to a very concrete example where I was involved, marginally I would say, with plenty of domain models and little machine learning, but it could easily become the opposite. UVR, then in Greifswald, at Bornscheyer's group, wanted to invert the enantiomer selectivity of a certain enzyme. Well, this is one of these images that biochemists easily read, and I look at it and I'm severely confused. But that was the result of the docking, and I could see that I don't see it really, but there are two pockets where the amine in a transaminase connects, and then he identified the residues that influence the pocket size and the pocket geometry. And the idea was, if it's enantioselective, well, if I just exchange the pocket characteristics, I could invert it. And so he selected these 7 residues, and then it defined by some fractional experimental design initial library, and synthesized the library and screened them. Okay. And then the results were collected. It was a certain variance. There was almost no activity towards R variance. Everything was S. And then he designed features. The one feature was a 2-number code for electronic properties and size. So for 7 residues, for each residue, so it's only a 14-dimensional code for each protein. And for the amine, he characterized when you split the amine at the nitrogen, you get the 2 groups, and for each group he designed one number for electronic properties, and then 3 more numbers for the size of the thing when you are more distant from the nitrogen atom. Okay, and then he used this thing to just use this as predictors and to predict the measured activities. And he used standard regression algorithms, just what is in the school box, scikit-learn plus XGBoost. He just tried the ones that are frequently used, and then did hyperparameter optimization for the SIN, and he's selected finally one that is really very powerful if you don't want to do modeling. Gradient boosted trees is a fairly robust thing and not so susceptible to the hyperparameters sometimes. And then he defined a generator for permutation library. Again, there was domain knowledge in it because he decided which of the 7 residues are most important. And he opted for 3 of them, and then you get 20 times 20 times 20 possibilities. And then in this library, he did a virtual screening using the algorithm he had trained. And then something I want to sweep under the carpet is that, again, it didn't really comply with ranking by the algorithm. He changed the ranking by some extra criterion, which he only found out when the data arrived. But this, when you write it down, you could actually put it into an ontological statement, something that could be made machine understandable. But I want to go over it. And then in the end, this was successful, and he found some heavily R. This red bar in the middle is the most active R variant that was found, and it's not completely enantiomer selective, but it's an inversion, and it's to a certain extent a success. And okay, and now again, what does this mean from this perspective of an automated research cycle? I wanted to present I'm building a package for some time. Have been building a package for some time that is meant to make it easy for people who know a little Python. It's not a graphical thing, but if you know just the basics of Python, you should be able to build models and to test them. That is the idea of it. And it takes some inspiration from the MLDE package from Francis Arnold's groups by Bittman and some others. And it's going to be open source together with Lada. It should be usable with basic knowledge, as I said. And of course, that is a critical point. Yufei tried out half a dozen models. Well, there are dozens of standard models around. And as we will see, with a bit more effort, you have thousands of possibilities of what to do. And just to choose one and to go with it is probably okay, but you would rather choose the best. So you would like an infrastructure which allows you to explore more of these things. It's not rocket science, but it would still could be fairly good models among this family. Okay, and it should be integrated with the lab workflow that is going to be created. First step of everything is how to get the data. And the first part of the model architecture should be an aggregator, which takes the data directly from the database. And therefore, it would have to have a semantical annotation. And I just want to explain how complex it is. Okay, I query sequences and substrates where an enzymatic activity was measured with respect to aminotransferase. Okay, maybe. But then, of course, maybe somebody deposited in the database information about important residues because somebody already did docking. So this docking information may be retrievable. So I don't have to recalculate it or could use it together with other results. And this querying of information is in a sense part of the model. Different models would need different types of information, like the model that Egon presented, where the docking geometry is part of the model. Okay, this is a thing one would have to build. And then I won't dwell too much on this, but we are lacking many standards. there is Strenda consortium defining what you have to report to really make an enzymatic experiment reproducible. That is, I think that the thing is fairly good, but it's not formalized yet, which means there is not a full data standard that implements it, but the enzyme ML, I think, is pretty close to it. And of course, if annotations are to be provided manually, it's hopeless. That's close to Alexei's comment that if machines do the work, you can force them to annotate everything. If humans do the work, you can't force them to spend, after 10 hours in the lab, 5 hours writing down the details they should have written down. So it's the kind of, that is one of the reasons why automation makes science better in some cases. Okay, and now, what is the data flow for training and prediction of such models? Well, you have the aggregated data. Actually, it has eliminated one of my slides. Oh, sorry, I was too fast. Okay, this was an aggregator picture, but I explained it already, so I don't have to show the picture. So, you verify and augment predictors. I think this is an important point. If information is lacking, for example, if a model needs the 3D structure, well, if it doesn't have it, you can run AlphaFold, RosettaFold, ASMFold, and hopefully use it, even though it sometimes goes wrong. Then you encode predictors. This is a very important topic, and there are many, virtually an infinity of possible encodings which made fare differently. And then something which few people observe, but I found it important, there are different ways of shaping the problem. I will say more about it. And then in the end, you get an XY representation of a regression problem. That is just a traditional thing. Try to fit a function that maps X to Y, and then you can train all low-level regressors that are already somewhere implemented, like in scikit-learn, simple packages, to run on this. But you can, of course, also run fancy neural networks. And then you get a trained regression model, and then you can use it again to predict. One thing I find important is that this is a modified data flow diagram. All the trained regression model and the aggregated data are themselves things that should be cached or stored in a database, because the trained model is, of course, an important entity, and it should also be annotated with semantic data to find it again, because you wasted energy to create it, and it's just stupid to train it again if you can need it. Okay, just have to look at the watch. Okay. And then this high-level model, this verifier component, encoder, shaper, and regression model. Okay, the verifier I just leave out because I have to cut through things. For the encoder, there are many options. The traditional thing is, if you know which residues are important, you encode them by physicochemical properties. There's AA index, a list of 100 and something amino acid properties. There's a sublist by Georgiev of about 19 physicochemical properties. And there are the 2 properties selected by Yufei. And so you can do this. Then you can use a multiple sequence alignment and use the distances, also a successful model, and basically it's the input of AlphaFold, for example. And then you can encode sequences by predictions of other models or intermediary presentations of other models. This is transfer learning. And the other models have been trained on something. Encoding information on the assays is essential if you start aggregating. Before not. If you are in one lab, you have the same assay, you can compare the data directly. But once you aggregate, you have different activities from different labs, which are not the same beasts, even if they have the same names. And therefore, it's very important to have this annotation too, in order at least for the models to discriminate between the different cases. So, and transfer learning, just to give an example, ESM2 is a very interesting type of model because it's first of all, it was first created as a pure language model. Just protein sequences with this masking approach that you try to predict parts of the sequence which you withhold from the model. Surprisingly, the internal representations can be analyzed and show many of the physicochemical properties of the folded protein. It's not a miracle, but it's interesting, and you might have expected, but it's really the fail. And they have built a folding algorithm on top of it, which is often on par with AlphaFold. Not always. But it's and for some cases even better. So it's really rich. And this representation is at present the best default thing for transfer learning. Will change next year probably, but now it's the case. And there's a recent publication by Fenoy from Argentina, and he just compared a few tasks, and ESM always was top for transfer And for UFA's case, I just found out it's actually as good as the special encoding by UFA, even if it's much larger in the dimension, which is a problem sometimes. Sorry. Another type of transfer learning, predictions of a model trained on one data set just to be used as a predictor for the other data set. And I did this actually a dumb thing. I trained one model on Egon's data, which are all transaminases, and on this common representation using this ESM transfer learning. And then I used the predictions of that model on UFA's data to use it as an encoder. And surprisingly, it worked basically as good as the other thing. It wasn't beaten, at least. So, okay. So this is also, and what I expect was a lift. I didn't get the lift, unfortunately, but this is also because the data set is very small, and it's difficult to detect lifts in small data sets. For subset encoding, it's even worse. We have more options. There are these molecular descriptors. I don't know whether you know the handbook of molecular descriptors by, what's his name, Italian? Todeschini. You know, it's like 700 pages and contains roughly 100 of these descriptors. And the WIM is an interesting case because it encodes geometry of different properties inside the molecule. So it's one that was quite successful in my attempts. RDF is a bit more simple. Substructure fingerprints can be important because if a substructure is relevant for an enzymatic mechanism, okay. And of course, yesterday in this talk about the conformers, if somebody gives me a model which tells me which conformers are most relevant, well, I could choose them and then encode these things. And of course, they are specially designed. There's plenty of them. And transfer learning is also possible this way, not only for proteins. Okay, inspired by UFA's thing, I designed the following descriptor. Well, I probably won't. I'd have that till 35, theoretically, about 30. Okay, bit far. I designed one thing. I just split using RDKit, which is a very useful Python package for molecule manipulation. I split the amine at the nitrogen. Then I get the two groups. And for each group, I want to have a description, a geometrical and electronic description. If I take just WIM, I get rotational symmetry. But I want to know where it is attached. So I just attach one other atom, a large one, a brom or so, to this place. And then I calculate the WIM. And this thing also proved to work quite well. I have to work on it still, but you can produce a whole family of enantioselective selective descriptors by this mechanism. Okay. And then, of course, you can stack these vector representations. There is, of course, a price to pay. You have always more longer descriptors with few data. So this is a general headline for small data, small n, large p. That's the name of the problem, and there are ways of dealing with it, but it's not hopeless, but of course it's a problem. Okay. I believe it's not a fundamental problem, but that's just an opinion. Okay. One thing that's also, in my opinion, transfer learning is just use physical simulations, chemical simulations, and attach the outputs as predictors. For example, the docking information, if you have automatic docking, you can just use them also as predictors. Or one example, a student of Marc Dörr is now using actually for transaminases too, and for the transaminases that UFA investigated, you know where the pockets are in this case. You don't have to do the docking. And then there is a program that fills the pockets incrementally to find out the volume of the pockets and also the geometry of the pockets. And so we can just build geometry and size descriptors for the two pockets, and we can attach them to the descriptors. And hopefully it will increase models that want to model enantioselectivity. selectivity. Okay, the shaper component is something perhaps not everybody's aware of. If I have n proteins and m substrates, one way to phrase it is I just map it as predicting the activity on all substrates from the proteins. So the X is just the stacked protein representations. But I can also do the following. I concatenate protein and substrate description, and then just predict one value. So one is a univariate problem, the other is multivariate. In principle, there's no difference. You can translate one in the other. But for standard models, there's a big difference. And so if you want to have a pluggable thing, it's important to have these different representations. This means I can now use standard regressors, but the package must provide automized cross-validation, of course, and something that is obvious when you do more than 1,000 experiments. or at some point your memory breaks down, you have to have good reporting, permanent retrievable reporting. You need a database where all numerical experiments are stored. People tend to know that they need a database for the experiments, but not for the numerical experiments. But the same thing. Everything should be documented so that you can retrieve it and analyze it with metadata. Okay. Now I have to skip a few things which are not so simple. The cross-validation is a crucial thing. And cross-validation is, in a sense, a simulated experiment. And therefore, the cross-validation has been the right simulation for the right experiment. If you want to find new enzymes, you should split across proteins and not across proteins and substrates. And if you want to look for new substrates, you have to do the cross-validation along substrates. And using the semantical information that is in everything, such a package should give you good defaults, because if the user that is not aware of it uses it, and use the wrong cross-validation, you just get the wrong results. Okay, I told the things that are written there, and therefore I don't have to show you this long slide. Okay, cross-validation for a collection of model is necessary because I have so many models. As you have seen, now I have. Okay. Okay, so I have. This is recorded, I'm told, so it's a bit embarrassing. The automatic, I need a meta model which generates automatic many variants of models, and then these things have to be screened. This is an enormous amount of models. Computation time gets larger. I have to be able to render in the cluster. Large amounts of training reports which have to be stored, and of course, you get a value. I get a distribution for each value. And then I have to take decision which I take, and I can't just take the largest mean. And the software package has to help with criteria to find this. For example, there is a recent idea to just use a Kruskal test on the sorted measurements to decide whether I can really distinguish with the batch ones. And if not, I take an ensemble of all the things I can't distinguish. And for last thing, if the data sets are too small, everything may be spurious. You can never be sure, even if you have a holdout set. Okay. And now, just to see what it means with distributions, this is an Egon's data set with just ignoring that it's different families of enzymes with this ASM encoding. And then for two different models, you get these distributions of the Kendall tau. This is a metric for ranking. And ranking is the important thing you have to do when you select the variance. So it's not, you don't have to have the right value, just have the right ranking. And then you get these things. And when you have 1,000 experiments, you get 1,000 of these histograms. And this perhaps illustrates why it's not easy to sort these things. Sometimes they are broader, but the mean is higher. And it really depends on the decision problem. If you have money for one experiment, you better choose the experiment with highest probability to be above a certain threshold. But if you have money for many experiments, highest mean is a good idea. Okay. And the typical, it doesn't look marvelous, but you see that the high values are indeed typically higher in their predictions. So if you use it for, this is just all the cross-validations superimposed for these two models. And this is across 7 families of enzymes, and it's still surprising that it's more or less grasping the relationship without any further effort. Okay. The metric, okay, it's actually, I'm over. Huh? Metrics are important, so I maybe should just say that the final picture was, that was what Mark Durr would have showed. Because he's building an architecture which is actually reminding very much of what the talk about the knowledge engineering showed, where different parts are, you have data standards for communication with lab devices, and you have standards for storing everything with semantic annotations. And somewhere in this, the machine learning component would be usable in the definition of a workflow, so that even people who don't know much about it should be able to use it. Okay, and so I skip a few things. And just the last remark, thinking of Ross King, AI is a strange word. Some people mean logical reasoning by it. Some people mean machine learning by it. And I think that it's actually true that in this domain, both are needed. And this is kind of maybe a relief for Ross King, that it's not only these statistical things that are prevailing. Okay, so now sorry, it's a bit too long. I thank everybody, the organizers of the conference, Mark Durr for many discussions, Egon Izon for discussions and his data, Yufei Hours for both Stefan, Mark, and the Kiwi Biolab people in Berlin.